Hello everyone, welcome back to Power System again. This is class number 8. Today we're going to talk about power unit system. This power unit system is a new concept for all of you. So I'm going to try to explain why it's needed first. In power system, you have a lot of equipment and all different voltage levels throughout the power system network. So it's get complicated if you try to use calculation for each section, because each section has different voltage level, different component, different equipments there. So in power system network, we put them all in a power unit system. What that means, we compare all of them to a base uh, measurements like base voltage, base current, base apparent power, and base impedance. So everything gets standardized against a base system. That is called power unit system. In power unit system, what the advantage is that you have a common point of reference for whole network, and also your voltage and current value becomes 0 to 1. Or maybe a little bit higher than 1. So 1 is the base for the system. So if your voltage is 1.05, that means you right away you know that at that point your voltage is 5% higher than what it should be. So you don't have to know what the voltage level is. That could be 20 kV, could be 100 kV, could be 600 kV, or could be just 120 volts. But based on the base, you know that is higher, 5% higher than what it should be. If it's per unit voltage is 0.95, then you know that is 5% lower than what it should be. It doesn't matter what value it is. And same with the current. And so in that case, you don't have to worry about different point, different voltage. You know that everything is compared to a base quantity. And so that is one other advantage is that all the generator transformer in the line reduced to an impedance. So your transformer is basically represented by a impedance, and also generator is represented by an impedance. So you have to also this system also simplify the generator and transformer connection in the system. So what is this? So per unit value over here is basically your actual quantity, right? And comparing with your base quantity. I said all of them has a base quantity. So for apparent power per unit, actual apparent power over here over base, B for base, and voltage is the same way, actual voltage over base voltage, current is the same way, actual current over base current, and impedance also actual impedance over the base impedance. So there's no base for real power and reactive power, because real power, reactive power could be derived from your apparent power. You know that as apparent power or complex power is P plus JQ. So if, as soon as you know that, you can find out P and Q from there. All right, so let's say three-phase voltage, volt ampere, MVA, megavolt ampere, and line-to-line voltage in kilovolts amp. So as you know that your S, if you know the line-to-line voltage and line current is, let's see, SB over here, B, IB, right? So then your IB would be this way. If you manipulate this equation, it would be like this one here. And your ZB, which is base line impedance for the transmission line, what I'm talking about here, you have a transmission line here, right? So let's say this is your load over here, and this is your generating over here, right? So this impedance over here, for the base impedance, it would be line to neutral voltage over here over the base current. So now if I modify these two equations, it becomes this equation over here. All right. So this is the voltage, right? This is just voltage. If I make this one kilovolts, and kilovolt square means what? Megavolts, right? Kilovolts is 1000, right? Kilo is 1000 volts. If I square it, I get 10 to the 6 volts. So this is mega, right? So if I square it over here, it becomes mega. So I can convert this one to mega to keep it with the unit. So that means your base impedance is basically a line to line kilovolts square over megavolts megavolts amp base. So line to line kilovolts base volt squared over megavolts amp will give you the base impedance of the line. This is for the line. So this is for the line. All right, and from there you can also see that your complex power is same equation, per unit voltage times per unit current conjugate, and per unit voltage is also per unit impedance times per unit current. So again, per unit impedance, as you have seen for the last one, is actual impedance over base impedance. And how to find base impedance is right here. That's how you find the base impedance. All right. Again, it's line to line KB. Let's put it emphasize over here. Is line to line squared over megavolts amp base complex power. So for example, if we have a line here for this line here, your base voltage is 100 kilovolts, right? And your base MVA BMVA is 100 megavolt amp. So then your ZV for this line over here, it would be 100 square, you can kilovolts square over 100. That will give you 100 ohm. That's your base impedance for that line. All right. So again, complex load is for the load is L is for the load here. L is for the load, right? So this is per phase. That's why I multiplied by 3. We're doing each phase voltage, phase current, and multiply by 3. Then your phase current, it will be phase voltage over phase impedance over here. P for the phase. P is for phase. Then your GP over here can be also find using this equation over here, right? And that could be converted to this one. This is the phase, right? So 3 BP squared can be also written as this, root 3 BP squared, and this is now become line to line voltage, right? So VLL squared, that's what we did over here, right? Can you see that? And this three phase power for the load. So that is your per phase impedance. You can find that equation, that one. And per unit, now you have the actual impedance over here divided by base impedance. Then you'll get this equation right here to find the per unit impedance for the load. And that is basically comes down to this equation right here. Complex. This is the complex load power. So for example, if you know the per unit voltage of the load, and also you know per unit complex load for the load, you can easily find per unit impedance for the load. All right, so let's move forward here. So change of base. Why is important to change a base? Everything needs to compare to the common base, right? For example, I'm going to draw a figure over here. Let's say this is your generator, and over here is going to a transformer, and you have a line over here. Then you have, it's a simplest thing you can do. That's a motor over here. So that's a simple line, right? So let's say it's a T1 over here, transformer 1, T2 over here. Let's say this whole thing is a Z, which is impedance. And then you have generator over here, right? So let's say your base for this system, base is 100 MVA, right? And we're using this voltage, let's say is 100 kilovolts right here. So 100 kilovolt base at the generator terminal. Generator terminal, right? So now, so this is the base. Now everything needs to compare to these two things over here, 100 MVA and 100 kilovolt base at the generator terminal. So now all other equipment, like you have motor, two transformer, line impedance, and even generator itself needs to be standardized against these two base. That's why your base needs to change. Now this is the base for the system, but each of the component has their own base when they're produced at the factory, they are calculated their impedance based on the base they used in the factory. Now you're bringing them into the power system. Now you have to change the base from their base to the power system base. This is the power system base right here, right? So that's called change of base. How do you do that? So one simple thing over here. So let's do this a simple example over here. It says that you have 115 34. So you have a low voltage side is this, high voltage is this. Transformer, the base of 36 kV selected. The base voltage on the high side must be this, right? What they're saying over here? Let's do this. So you have a transformer. Draw it first, then we'll see. Then let's say is there's a motor here, for example, right? So is this side is the transformer is this is a transformer trans ratio here 115, right, kV. So now if 36 volts comes on this side here, now if 36 volts comes in 36 kV, sorry, kV comes on the, what is the voltage over here? That's right here. So that 36 times, so on this side will be 36 times, what is the trans ratio? 115, 34.5, that will be 120 kV. So now, so this side voltage is 120, sorry, kV, and this side will 36. So now, if I do the calculation on this side, I have to do based on 120 kV. If I do the calculation on this side, I have to do the calculation based on 36 kV. That's what it's saying. So voltage propagates through the system based on the trans ratio of the transformer, right? So let's see how do you change the base over here. So the old over here, the actual value of this is talking about old means the equipment. So equipment comes with their own base. Equipment. So their actual impedance divided by base, that is then you know the what is this one is calculated is what this one, remember ZB, that is B squared over as B, right? So that equation right here. So that is your old one. New one is the power system. Now you're bringing the equipment to the power system. So now again is power system has their own base over here. Then it should be this one here now. So now you're trying to find the new one compared to each old one. If you combine these two, so new one over here, the old per unit, and as new, just basically modifying this two equation over here, you got this. So this one will give you the base impedance for the power system compared to the power system standards when you bring a new equipment to the power system. So if I bring a transformer or a motor to the power system, so this will give you the base impedance, per unit impedance of that equipment would compare to the power system base. All right. If you have the same voltage, so voltage will be cancelled over here, then you'll get only this one here, right? So this one is basically what it's doing. I'm bringing new equipment to the power system. So I'm gonna standardize that equipment impedance to the power system base. That's what it's doing over here. All right. So what is the abundance of per unit? Again, there is no relative magnitude, voltage, current, power, impedance all goes to a standardized comparison. There is no division of I don't have to know that particular bus or point has 100 kV voltage or not. If I know that voltage is 1.01, that means that particular point has a 1% higher voltage than it should be. All right. Narrow range of impedance range gets smaller, and there is no voltage levels, all disappears, and simplified power and voltage equations. Everything is simplified to the particular base. So we're gonna do this problem in the class, but I'm gonna do an example for you in the next video, so you'll be ready for the per unit problems.